Hello, welcome to this lecture. So today I am going to discuss about the uniform linear array. Okay, the uniform linear array is a category of array antenna. So the purpose of going for array antenna is to increase the directivity and gain. Okay, so we can increase the directivity of the antenna by increasing the length of the antenna, right? So if we increase the dimension of the antenna, along with the increase in the directivity, so we could get the reduction in gain. Okay, we want to increase the both the directivity and gain, and so we are going for the uh, array antenna concept. Fine. So array antennas are the arrangement of similar array elements, similar antenna elements in a proper fashion. Okay, so arrangement of similar antenna elements in a proper fashion. So it may be arranged in a linear fashion called as linear array, or it may be arranged as a circular fashion called as circular array. It can be arranged as a grid-like structure called as two-dimensional array. So we can have any type of array depending upon our type of application and the radiation characteristics requirement. Fine. So uniform linear array is the arrangement of antenna elements in a linear manner, and they are excited with equal amount of current, okay, equal amplitude of current, and they are having the equal spacing between the successive elements. So this type of array is called as uniform linear array. Okay, so we are seeing here the uniform linear array, the array of n number of isotropic elements. So isotropic element means these individual elements can radiate equally in all the directions. So such an elements we are arranging this as a array. So linear array. So we are arranging the individual isotropic elements in a linear array like that, and there are n number of elements are there. So these are the element numbers. So we have n number of elements arranged in a straight line, and this is called as uniform linear array, and the spacing between the successive elements is same, small d, and the elements are arranged along the axis theta is equal to 0. So this theta is equal to 0 indicates the z axis. So all the elements are arranged in a theta is equal to 0. And if we see the first element, due to the first element, there is a field created at a distance point P. So this P is the distance point at which we are finding the radiation characteristics. That means that we are going to estimate the electric field. So if we want to find the electric field at this point P, so we have to find the total electric field due to all the individual elements, right? So for example, if we denote the first if you denote the radiated field by the first element as capital E naught, okay. So as we have excited all the elements with equal amount of current, so the magnitude of current, excitation current is same. So this results the magnitude of the radiated field by individual elements are same. Okay. So radiated field by magnitude of radiated field by individual elements is E naught. So this is the magnitude of radiated field by individual elements, and the successive elements will have the radiated field that has the progressive phase shift. Okay, so that is the meaning of uniform linear array. Okay, so the radiated field will be having the progressive phase shift, and this progressive phase shift is denoted by psi, and this psi is the progressive phase shift. So the total field available, the total field radiated and that is available at the observation point, that is equal to the field created by each individual elements. So sum of the field created by each elements. So the first element is creating the field E naught. The second element is creating the field with the progressive phase shift of psi. So we denote this with E naught into e power j psi. Okay, so this is the field created by the, if you write the total field created by the array, antenna array, uniform linear array, so we can write E naught plus E naught into e power j psi plus E naught into e power j 2 psi. Likewise, it is going on up to plus E naught into e power j n minus 1 into psi. So this is the total field created by the uniform linear array, right? So we need to find the total. We need to alter this equation in order to find the total field created by the uniform linear array, and also we need to find the normalized radiated field. So this equation denotes the total field radiated by the uniform linear array. So this is the generalized expression, and psi is the phase shift. Okay, psi is the phase shift between the successive elements, and psi is denoted by beta d cos theta plus alpha, and beta is the phase constant, and alpha is the progressive phase. Alpha is the progressive phase shift. Okay. So we are having different categories of uniform linear array depending upon the radiation characteristics. So this progressive phase shift decides the type of the radiation characteristics. All right. So now we are proceeding to find the normalized radiation pattern. Okay. So if you multiply the equation 1 by e power j psi, we could get e power j psi into et. So this is the equation we are having, and one equation number 1 can be rewritten as, so if we take this E naught as common, we will get 1 plus e power j psi. Equation 1 can be rewritten as, by taking E naught as common outside. So Et is equal to E naught into 1 plus e power j psi plus 1 plus e power j 2 psi plus etc. plus 1 plus e power j n minus 1 times psi. Right. So let us keep this equation as equation number 3, and upon subtracting equation 3 minus 2, we could have E t 1 minus e power j psi. This is equal to, so we can have e naught minus e naught times e power j n psi. So that is equal to e naught into 1 minus e power j n psi. So this is the term we are getting. If we bring this term right hand side, so we have total electric field, that is total radiated field, that is equal to E naught times 1 minus e power j n psi divided by 1 minus e power j psi. So this is the form. This is one form of total radiated field. So this is the total radiated electric field, and this can be further modified as like this. So why we are writing in this, in the sense, we are going to find the normalized radiated electric field. Okay. So total electric field can be rewritten as, by by taking the e power j n psi by 2, by splitting this e power j n psi as e power j n psi by 2 into e power j n psi by 2, and in the denominator we are writing e power j psi by 2 into e power j psi by 2. Now we are taking this term outside, so minus e power j n psi by 2. So this quantity we are taking outside from the numerator, and from the denominator we are taking minus e power j psi by 2. So in the numerator this becomes e power j n psi by 2. So as the negative sign is taken over here, so this negative becomes positive, and since we have taken e power j n psi by 2, and the 1 becomes e power minus j n psi by 2. And similarly in the denominator, so we are taking e power j psi by 2 as outside. So minus e power j psi by 2 we are taking outside. So this becomes positive and coming over here, and 1 becomes e power minus j psi by 2. And we can simplify this term in the next step. So negative sign can be cancelled out. So this becomes e naught into e power j n minus 1 times psi by 2. And in the numerator, so if we divide the numerator by 2j and the denominator by 2j, there is nothing will change, and this becomes sine n psi by 2 divided by sine psi by 2. So this is the form of total radiated field. So this is the form of total radiated field, and this E naught is going to be the magnitude, and this represents the phase quantity. Okay, e power j n psi by 2 is representing the phase quantity. So this E naught is representing the magnitude. So phase of, let us denote this phase as phi. So phi is equal to n minus 1 times psi by 2, right? And this equation can be written as Et is equal to E naught sin n psi by 2 divided by sin psi by 2 into e power j phi. So this is the form of radiator field, and the phi is representing the phase of the phase of the radiator field, and this is the amplitude. Okay, fine. Normalized field is written by finding the maximum value. So this is the total radiated field. So this total radiated field is attaining the maximum value at psi is equal to 0. Okay. So maximum is attaining at psi is equal to 0. So if we substitute psi is equal to 0, this ET becomes 0 to 0 divided by 0 format, that is indefinite format. Okay. So this the ET becomes indefinite format. So in order to find the maximum value, what we are going to do is we need to use the L hospital rule. Okay. So that means we need to differentiate the numerator and we need to differentiate the denominator separately. Then we have to substitute psi is equal to 0. Okay. So separating upon differentiating in the numerator and the denominator separately. So we could have E naught into n by 2 cos n psi by 2 divided by 1 by 2 cos psi by 2. So given that the limit is psi tends to 0. Okay, so this is going to be the maximum value. Okay, so total electric field with psi tends to 0. Okay, so this is going to be the maximum electric field, and this can be obtained by using the L hospital rule. Okay, now if we substitute psi is equal to 0 over here, this will be unity, this will become 1 and this will become 1, and this can be vanished, and 1 by 2 will be getting cancelled. So finally we get the maximum value as E max as E naught into n. So this is going to be the maximum value of the radiated electric field intensity, right? So if we divide the radiated electric field intensity by its maximum value, we will get the normalized radiated field. So E normalized. Again, we are considering the magnitude. So normalized magnitude of the normalized electric field intensity, that is equal to uh, total radiated electric field intensity divided by the maximum radiated electric field intensity. Okay. So this is equal to E naught sin n psi by 2 divided by sin psi by 2 whole thing divided by n times E naught. Upon simplifying this, we will get the magnitude of normalized radiated field. This is equal to sin n psi by 2 divided by sin psi by 2. N sin psi by 2. So this is the normalized radiated field by the uniform linear array. Okay. So this normalized radiated field is otherwise called as array factor. Okay. So array factor is one of the significant parameter. That is the most important parameter for the array antenna for all sort of array antennas. So by calculating or by finding the array factor, so we can able to find all sort of radiation characteristics like radiated power, radiation intensity, half hour beam width, first null beam width, then so all the radiation characteristics like this can be estimated from the array factor. Okay. So this is the array factor for the uniform linear array. We stop here. We continue in the next class. Thank you for watching.